So today I'm going to put definitely an academic hat, and it's kind of a mini lecture on CO2 capture technologies. So my goal is for those who are not very familiar or not familiar at all with this kind of technology to have a better idea of what it is and maybe to understand why it's quite expensive also to run. I'm going to skip the intro. We know about the CO2 emissions, more than some people maybe south of the border. But and I want to go directly to the mitigation option. So there are a bunch of possible mitigation options, from energy conservation, fossil fuel switch, and I guess Ontario is a case in point by replacing coal by natural gas, by basically using to reduce the carbon intensity of the fuel, obviously using renewable, nuclear, forest sink. But what I want to focus on is on carbon capture and sequestrations. You mentioned my expertise in sequestration as well. That's not entirely true. I stick only to the carbon capture. Yeah. So because CO2 comes essentially from burning fuels that contains carbonous fuels, this is essentially done to produce energy usually. So there's a big spin on energy on what I'm doing. But if you want to look at the energy infrastructure, it's huge. So this is not something we can change overnight. And also, if you build those plants, they are here to stay for quite some time. So this CO2 capture and sequestration can really be viewed as, let's say, an intermediate measure until we can reach a situation where we can really deploy non-carbon emitting energy sources at a very large scale. So if we want to focus on carbon capture and storage, and I'm going to talk a little bit about utilization as well, there are three main components. First, you need to capture the CO2 from where it is emitted. Then you need to transport the CO2. And finally, you need to store the CO2. Every of those areas, I mean, you have like specialized people working on every of these areas. And if you look at the cost, the capture of the CO2 is usually by far the highest cost in this process. So this is where maybe savings could be done, and this is where a lot of research is being done to try to find better way to capture CO2. Now, if we look at utilization, and you will see it's basically using CO2 and making something out of it instead of storing it underground. It's pretty much the same. You have the capture, the transport. The transport could be significantly shorter, especially if you have a plant nearby, and then you have a process to use the CO2. What you have to realize is when you burn stuff, the composition of the flue gas can vary significantly from the process you use. So this is an example. So if you just want to focus on the CO2 concentration, if you burn from a natural gas turbine, you have only 3 to 4% CO2 in the flue gas. If you burn in a coal, it goes up to 14%. If you use a cement kiln of gas, then it can go much higher. So depending on the concentration, you might have different way to capture CO2. But mostly the bottom line, if you look, those are still fairly low concentrations. So the key here is to deal with how to basically separate relatively dilute amount of CO2 from a flue gas that may contain a bunch of impurity. So this is a very nice schematic that comes from the IPCC special report on carbon dioxide capture and storage several years ago, although it's still very valid to this date. So I'm going to describe a little bit what this is about. You can have a whole suite of other kind of technology being developed, but those will be some, especially the first three, the three main ones. So this is really, if you burn something, so since we are talking about waste recovery, It could be if you burn, I guess, waste as well, not only natural gas, coal, or biomass. So you have three main aspects. So you have post-combustion, pre-combustion, and something called oxy-fuel. Post-combustion is probably the simplest to understand. This is you burn your stuff, you have a flue gas, and you need to separate. So it's a kind of, it's an end-of-pipe solution. And then you have to compress the CO2 and do something with it or utilize it. But this is the benefit of the post-combustion is that you don't have to touch anything on your existing device that generate power and heat here. So you, in quote, you can just add these at the end. On a pre-combustion, maybe I'm going to say very few things. It's not too relevant to Ontario. This is more if you burn coal, possibly biomass, where you will gasify your coal, means you don't burn it completely. You react with steam and oxygen, and you basically make the carbon into mostly carbon monoxide, the hydrogen inside, because you have hydrogen, by the way, in your coal, into hydrogen, and you have a few more other steps where you end up basically making hydrogen that you can separate from CO2, which is not too difficult. Yeah, so one of the big difficulty actually in the first one is to separate essentially carbon dioxide from nitrogen. This is a very costly operation. To separate hydrogen from CO2, this is not as difficult to do. Then, because the main point of here is to separate nitrogen from oxygen, people say, but why not getting rid of the hydrogen up front? And that's basically what's behind the oxy-fuel. That's what's oxy-fuel. So in this case, you will need to separate air. You have an air separation where you separate the oxygen from the nitrogen, and you basically burn your fuel with oxygen. And in that case, you get a fairly high purity CO2 at the end. So it looks good in principle, but it's way more complicated than that. So I'm going to go relatively quickly on this. You have several ways for this post-combustion capture. So if you take a flue gas, the most common one will be a so-called chemical solvent. This one is actually a very mature technology. It has been commercially available for more than 60 years. It's routinely used in some chemical processes, but not at the scale when it comes, let's say, for a big power plant. And now, if you really want to capture CO2 at a very large scale, there are very few actually technology at that scale available, and probably this is one of the few choices you really have. So in that case, chemical solvent, I mean, just a quick little, CO2 is reacting chemically with the solvent, so you have a very strong bond. Physical solvents, these will be more suitable for high pressure systems, so in that case, the bonding is not as strong, and you have other technique where you can separate CO2 from nitrogen in the end. I just want to show you a little bit. I guess I'm in chemical engineering, so I have to show you a plant like that. This is really the most mature and common technology to separate CO2 based on chemical solvent, and maybe you might hear sometimes amine based kind of system. That's pretty much what it is. You have several kind of amines where basically, so for those who are non-technical, hopefully you can boast after you understand this system. So this is where the gas come here, and you have the solvent that come from the top. The solvent is going down, the gas is going up, and they mix. CO2 react with the solvent, and that solvent that contains a lot of CO2 is going to another column, and here we have a gas that's depleted in CO2. Then in the other column, we do the reverse, where in this case, we have to re-separate the CO2 from the solvent, and this needs some heat. And this is where this thing is getting very expensive because you need a lot of heat. So most of the cost of a system like that will come to the heat required to regenerate the solvent, which is sent back to this one. So you have, so I heard a lot about what cycle economy or something. So here it's also a lot of cycles as well. Yeah. I'm going to skip. Oxy-fuel combustion, it's an interesting process where, so I mentioned you need to separate the nitrogen up front. You burn with oxygen, but if you burn oxygen with a fuel, it's going to be really hot, and your material won't be able to accept this temperature. So you need to find a way to cool down the temperature, and you do that by recycling part of the flue gas. And that flue gas contains mostly CO2 and water. One benefit of doing these things is that the flow coming to the CO2 compression and purification is much smaller than in another system. So there is a scale, you scale down and you can save some energy. But here, the big cost is in the air separation. You need for a normal, maybe 400 megawatt plant, you will need 2 to 3 of the biggest cryogenic-based air separation you can find. So everything is huge. Something else that has been becoming more and more popular over the last couple of decades is so-called chemical looping. So you might have heard this, or you might not. It's a system where you need 2 reactors, another of those cycle things. In one, so you have basically a metal. It's kind of a sponge, but this one a sponge for oxygen. You have a metal coming to react. Let's say you have a metal with oxygen, a metal oxide. Go to a reactor. The oxygen in this metal oxide react with the fuel, generating, so the carbon in the fuel becomes CO2, the hydrogen in the fuel becomes water. So you make essentially CO2 and water, which is easy to separate. And then you have to recycle back your reduced metal that you re-oxidize in another reactor. So these people have done some studies, like on paper, if you can make this work, it could reduce significantly the cost of CO2 capture for energy production. But a big deal is about this metal oxide, who has a tendency to lose a lot of activity over those cycles. I'm going to skip the efficiency. So I'm not in the economics, but this is the only time I'm going to talk about dollar. When we try to compare system for CO2 capture based on some sort of economics, there is a concept of dollar of cost of CO2 avoided rather than cost of CO2 capture. It's a little easier to make comparison, and that's the way it works. Imagine so to do that, you need a reference plant. So you have your reference plant. Let's say you have a normal natural gas power plant, and that plant will produce this amount of CO2, all the salmon color here, and the cost of electricity will be something. Then you say, I'm going to build a plant, the same kind of plant, but I put a CO2 capture on it. In this case, the amount of CO2 will be much less. I mean, typically people are looking at maybe 85%, 90% reductions. And all of this extra CO2 will be the CO2 that will be captured. So the CO2 avoided is really the difference between the CO2 that's really being emitted to the atmosphere. And then the cost of CO2 avoided will be basically the difference of cost of electricity between these two divided by the difference in emissions. So it's a little different. If you do that and you compare different technologies, so here it looks that there may be some winner and loser. You use, because this is a certain source, you use another source, you will find something different. The key now, you cannot really say that technology is so much superior than the other one. That's why you have so many people working on different areas. So all what I talked about now was to capture CO2 from a flue gas of some sort. Something that's kind of interesting, but there are a lot of debates about the feasibility of this, is to basically capture CO2 directly from the air. So you have a few companies working on this. I mean, one of the pioneering one is Carbon Engineering, so it's a Canadian company, so might as well mention it. And well, they have a system, basically, where they can capture CO2. So now you have to see the difference. Now we have only 400 ppm of CO2 to capture, as opposed to maybe 10%. So it's a huge difference. Well, people are going to argue about the economics of such process, but maybe something that's quite, maybe if you look in the future, long-term future, in the event we cannot reach the 2 degree, we get a little more because we emit more than we think we would be able to do. This kind of technology can actually remove CO2 even long time after. So that's how people can sell this kind of things. Now, because this workshop is more about waste, so I try to see where we can link CO2 capture and waste. So you have all these waste to energy plants. I mean, we heard about that. So basically, you make. And according to the EPA, the CO2 emission from those kind of plants are somewhat similar to a natural gas plant once you take into account the biomass you can reduce the emissions. But I have found one example where people are trying basically to add a capture system from an incinerator, and this is in Norway. So they have near Oslo. They have an incinerator, and it's not like a full scale. So this was done, I guess, last year, sometimes last year. So they have an incinerator that emit over 300,000 tons of CO2 per year. That's what they emit. And they try to make a pilot test where they could try to capture 2,000 tons of CO2 capture. And apparently this test has been successful, but it seems they are working on further study to see if they can go to full scale. Obviously, cost is a major issue here. Now, one of my last slides, it's what you do with this CO2. I mean, it's good. You can capture the CO2, but what you do after. And this is where you have the CO2 utilization or storage that comes into place. So the storage, so you have enhanced oil recovery, so that's a big one. Here, you seem to have a lot of things here, but you have to realize many maybe are very interesting from a business aspect, but they are too small to make any significant difference. So the ones that could make a difference in terms of CO2 utilization, where you need large amount, will be this one. You can also, you cannot see very well from here, you can produce some chemicals. This can be quite big. You can mineralization, also carbonates are a big one. Also something that's very popular, more and more popular, using algae to make biofuel. Those are also very promising one. So I would like to show you maybe just one example. I have three, but in the sake of time, this is probably the most interesting example for an audience like we have here. So we are working with a company called Advanced with the Typo Chemical Technology on a process here where we try to use CO2 as a feedstock to ultimately produce methanol. So you will find some people have put this kind of process. You bring CO2, you have hydrogen coming possibly from, usually from an electrolyzer. So it's hydrogen that didn't emit much carbon dioxide. You kind of mix those to make some product, and typically methanol will be a good one. So here, it's to make methanol, you need hydrogen and carbon monoxide. So you need a source of hydrogen and a source of carbon. Our source of carbon is still primary natural gas, like a normal methanol plant, but with some CO2, and our source of hydrogen is still a little in the natural gas, but also in water. So we have a kind of a system here. And so this is where the CO2 here, we are looking at a possible site with a nearby plant, and we are currently looking at how we can implement the purification of the CO2 as well. This process in itself generates some CO2. We can capture the whole things to have a plant that is negative, is at least zero emission, if you take into account the CO2 capture, or possibly even a little bit negative emission of CO2 to make methanol. And I'm going to skip the rest, and I want to thank you for your attention.